Okay, here. So let me start from sharing the video. Sorry, sharing the desktop. Okay, here we go. And so again, so we're doing basically part one. Okay, maybe let's do this. Okay, so yeah, we will end up. We'll probably finish chapter 8. I don't think we have time for chapter 9, especially for this kind of a really condensed summer section. Yeah. So this today we're starting to talk about rotational motion and gravitation. Okay. Okay, so what is the topic here? Again, remember we're doing mechanics, and pretty much from chapter 2 to chapter 3 we did kinematics, and chapter 4 basically is Newton's law, which is dynamics, and then we did chapter 5 and chapter 6. These are basically advanced concepts. Basically like energy and momentum. Notice one common feature of these two chapters is that we share the I mean, they both have a conservation law, conservation of energy and conservation of momentum. And I mean, it's, in both chapters, this is the most important thing. And it allowed us to solve some problems without going to dynamics and Newton's law. So we can kind of do them like a little bit easier, you know, more convenient, so faster. And that's the reason we introduced them in the first place. Okay, now starting from this chapter, what we're gonna do for chapter 7 and 8. We're gonna, instead of talking about these advanced stuff, we're gonna talk about a specific kind of motion, which is rotation. Okay. So far, what we talk about in kinematics and dynamics, all the quantities we introduced applies for all kinds of motion in general. Okay. Now Newton's law also applies to rotation, and the quantities we have here, like displacement, velocity, acceleration, they all can be used for describing rotations. However, it turns out because of the special nature of rotation, certain quantities or new quantities are more convenient to have, and they, I mean, tells us a lot of good things. Okay, so so that's why we want to talk about these two chapters. Okay, now if time allow, when in chapter 8 we'll introduce another quantity, kind of advanced concept, just like energy and momentum. In chapter 8 we will talk about angular momentum if we have time. I bet you guys feel like we better not talk about it, you know, because too much material. But that's kind of similar, plays similar role as momentum for linear motion. In case of rotation, we have something called angular momentum, which is actually help us to, we can use some conservation laws. I think we can at least talk about it qualitatively. Okay. So the point here is, so we're gonna go to rotation. Okay. Now, what do we do in these two chapters? Okay. In some sense, we're gonna repeat the whole thing we did from chapter 2 all the way to chapter 6. Okay. So we're just like doing a different cycle just for this specific motion, rotation. So in chapter 7, we'll talk about mostly dynamics. I mean, sorry. I mean, the ring totally put me off. So let me raise it. Okay. We'll talk about kinematics of rotation and a little bit of dynamics. Okay. Well, in chapter 8, we'll talk more dynamics, okay? And then we'll talk a little bit energy. And then as I said, if we have time, we'll talk about angular momentum. So in some sense, in chapter 7 is like chapter 2 and 3 and a little bit chapter 4. And then chapter 8 is like a little bit chapter 4 and then chapter 5 and 6. So it's kind of, as I said, it's kind of repeating the whole cycle again, okay? Because of this, these two chapters, although the materials are new, these two chapters are not very like terrible, I mean, to absorb, because we're kind of doing similar things as we did before. So it's not the idea or the logic aren't totally new. So in this sense, I hope you guys feel a little better, okay, for these two chapters. So let's get started, okay? Let's go back to chapter 7 and start talking about chapter 7, okay? Rotation, motion, and gravitation, okay? Now, the first question is, why do we want to consider rotation, right? Why rotation is so special? Why do we want to spend a lot of time on rotations, okay? Well, the basic answer is we have we have a lot of rotations, this kind of motion going on in our everyday life and in our, I mean, a lot of, I mean, in physics as well. Can you guys give me some examples of rotations? Maybe you can either say it or send me a message. Like some rotation you can think out of your mind, you know? Right, I mean, right now in your mind.
You mean like a ball? You throw it or kick it or whatever?
Okay,
Or
a ball,
different?
yeah. Well, yeah, a ball definitely can rotate, right? Like, and pretty much the way the ball moves is rotating, right? So certainly that's rotation. Anything else? Okay, I got a message. Shorter rotation, what does that mean? It means like this. Is this what you mean, shorter rotation? I don't know. Or like this? Or, sorry. I'm sorry, like this, right? Is this like shorter rotation? Okay, yeah. Okay, certainly, yeah. Yeah, certainly that's one kind. Yeah, there's all kinds of others like well. For example, if you have a old-fashioned clock, not the digital clocks, right? But you have like a clock with like all those handles on it, you know, ticks, right? Those three handles, they go around the panel. This is the rotation, right? And the wheel, right? The wheel certainly is doing rotation, like a wheel on a car, or like like those like those new, like, what is it called? Like this is called like fans or something, like for I mean, certainly the fans are like this, like electric fans, but there's also this
Like a
kind of
windmill?
thing. Say it again.
A windmill?
Yeah, the meal. Yeah, yeah. What I really want to say is like when you go drive to some rural area, you'll see a bunch of these very high towers with huge fans on top of them. They're
Yeah,
like for the
windmills.
yeah, windmill, right?
Yeah.
Windmill, yeah. For like you can produce electricity by using the wind power. So that kind of thing, right? There's certain rotation, and actually, as we know, the Earth is rotating, right? This is why we have day and night, okay? And also the Earth not only rotates by itself, the Earth also rotates around the sun, okay? Do you guys know the shape of the orbits of the Earth rotating around the sun? It is not
So it's more of an oval.
Yeah, it's oval, but better and more precisely, we call it elliptical, right? It's an ellipse, okay? Well, it is a rotation as well, although it's not on a circle, but it's still a rotation. So there's all kinds of rotation we have, and so if you look at these kind of those rotations, what are the common features here? Basically, one thing you notice is all kinds of rotations are periodic motions. Okay. So in the sense that after one period, this the object goes back to the original position and then start new cycle. And by the way, this generate for us the years, right? Each time the Earth go around in one cycle of the sun, this is 1 year, what we call 1 year, right? Well, for a normal human being, we can experience this period for about 70 to 100 years, 70 to 100 times. That's about it, you know. And then we have to die. And then, but that's still very good way to measure time because it's like, it determines the seasons and everything when you go through the year. So all the rotations are periodic, and that actually is kind of important nature feature for rotations. Oh, yeah, sphere, you can rotate as well. Yes. So, so I just kind of give you guys some example here. So when you think about rotation in this chapter, what I want you to think about is something like this. Okay, this might be, the simplest rotation possible. Okay, so think about a particle. Okay, going on a circle. Well, you can think about this maybe electron going around a nucleus, but although in the real world, the electron does not go like a circle, exactly like a circle, but still, this might help you to kind of picturize how this moves. But anyway, this might be like the simplest rotation possible when you have a single particle going on a circle. Okay, so now let's go ahead and talk about the kinematics of the rotation, which is we want to find out all the possible or very useful quantities to describe rotation. Okay, so again, this comes from our intuition, right? So when something rotating, right, and then in the simplest case, rotating in the plane, like in a circle, the question is what kind of quantity we should use to describe it, like this, right? This is rotation. Okay, maybe send me a message. Tell me, what do you think? What kind of quantities? Now remember, what we can draw some analogy from chapter 2 and 3. In chapter 2 and 3, we learned about 3 quantities, right? We have a displacement, delta x, and then velocity v and acceleration a. Okay, so we have these 3 quantities, basically, to describe motion. What can we introduce in the case of rotation that's kind of similar to those? Anybody? Just send me a message. Okay, I got some. It's a combination of all of them. What do you mean combination of all the 3 quantities? We actually need some new quantities. So the reason I wrote them here is just give you some like inspiration so that you can maybe think about along that direction. But we do need we need to use totally new quantities. Okay. Anybody? For example, what kind of a thing we can use to describe the position change of this object on the circle? Okay. Okay. I guess, I don't know. Seems like this is the problem is like going through it. Okay. Yeah. Radius and circumference. Okay. That's a good starting point. Okay. Radius, definitely, if you need to know about the circle, you need to know the radius. Okay. This gives you the size of the circle. And then circumference is actually not independent of radius. As far as you know the radius, you can calculate circumference by using 2 pi r, right? But even if you know the radius, it only specifies this circle, but how do you know where the object is on the circle, right? You need another quantity to specify that, right? Okay, direction, angle, good, yeah. Angle is kind of the thing I'm looking for, but yeah, great, okay. So again, let me say this. So when we remember what we did in chapter 2, we start from the simplest motion possible, which is a motion happens along a straight line. That's kind of one-dimensional motion, right? Same thing for rotation. We'll start from simplest rotation possible, which is essentially this rotation I'm talking about. But think about it, you cannot have rotation in one dimensional, right? You cannot rotate something on a straight line. It's just simply impossible. So the simplest rotation we have has to be a 2D rotation, okay? 2D rotation, okay? That's kind of analogous to 1D linear motion, okay? Now, to describe this kind of rotation, like this picture shows you, we need a angle here for sure, okay? So the angle is defined like this. Conventionally, it's defined as the angle between, I mean, you draw the circle, I mean, the center of the rotation, and then you draw a line connecting the center to the object. That gives you one direction, and then you normally define another direction going just positive horizontal direction, okay? That angle between these two directions is the angle we define, okay? So, and correspondingly, we call theta angle. This is kind of like x, which is a position, which talks about tells position, okay? And then we can talk about delta theta. This is called angular displacement, okay? Again, this is analogous to delta x, which is simply displacement. And then we can talk about something similar to v, which is omega, which is defined as delta theta over delta t, okay? It's called angular speed, angular velocity, okay? And I mean, this corresponds to v equal to delta x over delta t, which is simply velocity. Finally, we can talk about something similar to acceleration, which we call alpha, which is delta omega over delta t, which is called angular acceleration. And then we have correspondingly A in the previous case, which is defined as delta V over delta T. Okay, so I mean, you can see kind of the analogy here, right, between these two cases, okay? Now, those quantities are really like one-to-one corresponding to each other, okay? Notice that the name of the new quantities we have very similar to the old ones, except we put an angle or angular in front of it. So this is angular displacement, angular velocity, angular acceleration, okay? So these are all about angles. Well, these things here has no angles, okay? And another thing you notice here is like the letters we use here to define rotational quantities are all Greek letters, okay? While these ones, the X, the T, V, and A, they're Latin letters, right? So they're different. And for example, this one is not W, okay? A lot of people want to call this W. It's not W, it's omega. So when I write W, I would write like this, okay? Well, when I write omega, I write like this. Can you tell they're totally different, right? Maybe not that obvious for you, but see, when I write omega, I try to make them like curled, you know? So, and this is alpha, it's again another Greek letter. So some of you live in those traditional like dorms, or maybe you join a society in the school. Sometimes they label those, they name those societies with Greek letters, like the sigma, pi, sigma, or alpha, beta, alpha, whatever they are, you know. But these are all Greek letters. Okay, it's just kind of convention to use all the Greek letters for rotational quantities, while use these for linear quantities. Okay. Any questions? Well, their meanings, okay, let me, I mean, we introduce them really quick here, but let's go through them one by one and to make sure we understand them, okay? Let's start from the angle theta, okay? Let me see, kinematics, okay? Maybe I'll call this one. Now for angle theta, we want to talk about introduce a new unit, okay? Angle. Now, so far in this class, we've been using degrees, okay? In your calculator, you need to make sure your angle was in degree mode when you do some calculation, use sine, cosine, or whatever. But now in this chapter, we're going to introduce a new unit. New unit is called a radian, okay? So how many of you have learned about radian before? If you have learned about radian, give me a thumb up. Okay, 2, 3. Okay. Honestly, even if all of you have learned it, I still need to talk about it because I'm sure some other people in this class haven't learned it yet. So let me talk about radian again. Okay, again, this be for some of you, this may be just a review. Okay, so how do we define an angle in radian? So again, consider a circle. Maybe let me draw like in a solid line here. Okay. So a radian angle, like say this angle theta, right, is defined like this. So take the arc length of this this part of the circle, which is I call it S, divided by the radius of the circle, we call it R. So this gives you definition of a radian. So S divided by R, okay? Arc length divided by the radius, okay? So the advantage of defining a radian, defining angle like this is you have a length here divided by another length. So all the lengths are measured in meters. So you basically have meter divided by meter, right? So strictly speaking, radian is just a number. So you have meter divided by meter, okay? So they cancel out. So you should actually get just the number. But for convenience, people call it radian, although it's really just a number, okay? Now, we know for the full circle, right, the circumference of a circle is given by 2 pi r. So for the full circle, the angle is 2 pi r divided by r, which is 2 pi. So that tells you that there's a relation between degree and radian, because we know for the full circle, it's 360 degrees. So 360 degree corresponding to 2 pi radian, okay? So we can set up a table kind of help us to see the connection between the two units. 360 is 2 pi, and then we have 180 is half of the circle. You divide by 2 here, same thing here. So 180 degree equals to pi radian. And then you divide it again, you have 90 degree, it'd be like pi over 2, okay? And then you can divide this by 3, you got 60 degree, that'll be like pi over 3. And then you divide 90 by 2, you have 45 degree, it's pi over 4, because this divided by 2 is just another 2 here. So, and then finally you have 30 degree, it is half of this, so it's going to be pi over 6. Okay, so this table kind of help you to see the correspondence between these 2 degrees. Now I don't know which one you like better. If you don't have a lot of intuition about radian, but you have a pretty good intuition about degrees, this table may help you to feel the value, how big they are in this new unit. Okay. Now, the reason we want to introduce this new unit is it is kind of convenient for us to talk about a lot of things, as we'll see a little bit, okay? So these are the angle, right? Now let's talk about a little bit angular displacement, delta theta, right? Well, there's not much to talk about except that we can define delta theta as theta final minus theta initial. Okay, notice this is very similar to displacement, right? Displacement was defined as x final minus x initial, right? So they're kind of similar. One thing you do notice here is very as similar to this case, this angular displacement could be either positive or negative, okay? If this is delta theta is larger than 0, it's positive. I mean, smaller than 0 is negative, right? Well, what does that tell us? Again, it's kind of similar to the case of displacement. It tells us which direction the object rotate, okay? So the convention in case of angle is whenever, if you start from the positive direction, horizontal positive direction, if you go counterclockwise, the angles are positive. For example, this is maybe you can call this one like 60 degree or pi over 3. If you go so this is counterclockwise. If you go clockwise, the angle is negative. So like this one here, maybe negative 30 degree or negative pi over 4 or pi over 6. Okay. So this is kind of convention here. So based on this convention, if the final angle is larger than the initial angle, that means the object is going counterclockwise. So delta theta is larger than 0. It's a rotate counterclockwise. Well, if delta theta is smaller than, let me erase it. If delta theta is smaller than 0, it means rotate clockwise. Okay. Well, you can easily check, right? For example, if you say your theta f is 120 degree and theta I is 30 degree, right? Then delta theta is equals to 120 minus 30, which is 90 degree. Well, that means this thing will go, from 30 to 120, so it's going counterclockwise, right? Again, here I use the degrees because I think sometimes, we can use both, but it's sometimes more convenient to use one compared with the other, but it doesn't hurt us to use degrees. Anyway, so this basically tells us kind of all I want to say about this new quantity. Very similar to the previous one we learned, but though it can be positive or negative. It tells us about the direction of this rotation. So based on this, what would you say? Is angular displacement a scalar or is a vector? Again, send me a message. Okay, I got one answer. Okay, two answers. Okay, vectors. That's right, because it has both direction and magnitude. And again, because they're very analogous to this angular displacement, so it should be like that, Okay, so that's about the angular displacement. Now, next, let's move on to angular velocity. Omega, okay. Again, by definition, omega equals to delta theta over delta t, right? This is very similar to v equal to delta delta x over delta t. So basically, very similar to v, omega would be just something to measure how fast the rotation is, right? The bigger omega you have, the faster this object is moving, right? So certainly that's a pretty clear physical meaning. And again, you could have a direction. So maybe let me put it here. Delta theta is a vector. Okay, now here again, because delta theta is a vector as we discussed, omega would be a vector as well. And the sign of omega simply tells you which direction the object rotate. Could be counterclockwise or clockwise. Okay. Again, you see the analogy to the one-dimensional motion here. So there's only two directions basically, right? For two-dimensional rotation, you can either go counterclockwise or clockwise. Well, similarly for one-dimensional linear motion, you can either go to the right or to the left, and that's about it. There's nothing else. So in each case, you just have these two directions, and that's why 2D rotation is very similar to 1D linear motion. Okay. And okay, for the unit, right, because theta is measured in radians, so omega would be radian per second. Okay, just divide this. Because radian is not a real unit, because essentially length divided by another length, so it's actually sometimes people would write as s-1 as well. Okay, because this is really not a real unit. Okay, and the physical meaning of angular velocity is pretty clear. You just draw an analogy to the previous case. Okay. Now finally, let's talk about angular acceleration. Okay, alpha. Okay, which is defined as delta omega over delta t. Okay. So again, okay. By the way, sorry. This is a vector, right? Vector. So this is very analogous to a, right? Delta v over delta t. And the physical meaning are similar again. The a here is measures the how fast the velocity changes. Well, alpha measures how fast the angular velocity changes. So again, you could have positive or negative values for alpha that just tells you how how your angular velocity change. It could be increasing or decreasing. It depends on the signs and everything. Okay. So and the unit here is again gonna be just this is radian per second, so radian per second square. Okay. Or sometimes just s-2 because radian is not a real unit. A real yeah, it's just like a sign basically. And again, this will be like a vector. Okay. So any questions? I went through everything here pretty fast because, I mean, it's kind of really similar to what we had before, you know, for one-dimensional linear motion, you know. So, but if you guys have any questions, send me a message. I can explain. Do you guys feel like this quantities are kind of okay to understand? They're not totally new, right? Give me a thumb up if you feel like it's good. Okay, great. Okay, so let's move on then. Okay, so again, we follow what we did in chapter 2. We'll talk about two kinds of specific rotations. Okay. And if you remember what we did in chapter 2, we start from the simplest linear motion here, which is a constant velocity motion. And for rotation, that will be called a constant angular velocity motion. And well, think about what's going to happen. If the angular velocity is a constant, that means omega is constant. So this thing going to rotate with this basically same rate and going along one direction forever, you know, like this, you know, like just going around again and again and again. A good clock, you know, the ticks on the good clock would be the, I mean, the handles on the good clock would be just like that, you know, because the good clock is supposed to be like rotating constantly with the same rate. So, and there's another name for this simplest rotation, sometimes called uniform circular motion. Okay, just different name. Now again, we can solve some problem in this case, but it's not much because basically just this formula here, there's no constant acceleration, right? There's no angular acceleration. So if you know the angular velocity, we can calculate the angular displacement by writing things like this. Okay, delta theta equal to omega times delta t, right? That's pretty much it. And yeah, so well, the second one we want to talk about is again similar to what we did in chapter 2. Will be constant angular acceleration motion. Okay. Well, in this case, what is constant is not the angular velocity itself, but the angular acceleration. So the object would rotate, but it's going to either rotating faster and faster and faster, or slower and slower and slower. Okay. And but the acceleration stays as constant. Okay. Well, you may see these kind of rotation. For example, when your car speed up from 0 to like whatever velocity speed you want it to be, during that process, the wheels rotate faster and faster. Or when you press the brake right on the car, so the car slows down. That during that process, the wheel rotates like slower and slower. Those kind of things are kind of like the case we're talking about. So let me see. So, and again, we could develop all these formulas as we did in chapter 2. And they're very analogous to what we talked about before. So let me write down the formulas before, and then I'll just write down the new formulas. Okay, so the formula before we have, for example, we have VF equal to A plus, VI plus A delta T. Okay, maybe let me erase that one. And then we have del x equals to vi plus vf over 2 times del t. And then we have del x equals to vi del t plus 1/2 a del t square. Then del x equals to vf square minus vi squared divided by 2a. So if you remember, these are the four formulas we derived before for constant acceleration motion. We could actually do the same for the constant angular acceleration motion, but the simplest thing to do is just simply replace the quantity with corresponding new quantities. For example, here we would replace v by omega, so we have omega f equal to omega I plus alpha delta t. So we replace a by alpha, v by omega. Second one, we have del alpha equals to omega I plus omega f divided by 2 times delta t. I'm sorry, this is not delta alpha, this is delta theta. And then third one, we have delta theta equals to omega I delta t plus 1/2 alpha delta t squared. Finally, this one, we have delta theta equals to omega f squared minus omega I squared divided by 2 alpha. Okay. Yes. So does that make sense, you guys? Well, we can go ahead and derive them, but the process will be really similar to what we did in chapter 2. And also for you guys, I mean, say, for example, this one's here just come from definition of this angular acceleration. And then after that, this one is kind of like a special feature of constant angular acceleration motion. And you plug this one to this one, you get this one. And then finally, you plug delta t to here, from here to here, solve for delta t and plug it here, you get this one, okay? So that means we can solve similar problems as we did for constant acceleration motion, like the way we do for constant angular acceleration motion, okay? And let me maybe talk about an example, okay? We're not gonna go through the whole thing as we did in chapter 2 because this is already something we kind of know, okay? But I think it still makes sense to give at least one example, okay? Again, if you guys have any questions, let me know, okay? I can always slow down. Let me go like 200. Okay. Okay, this is rotational motion, okay. Okay, so let's do one exercise example. Let's do this one, okay? A rotating wheel, okay? Let me see, is that a good one to do? Okay, yes. Okay, so in this problem, you have a wheel rotates with a constant angular acceleration 3.5 radian per second squared, okay? Now the initial angular velocity of the wheel is given as 2 radian per second. And then ask how much angle has been rotated through this 2 seconds, okay? It asks you to give the answer in both in radians and revolutions, okay? And then B, what is the angular velocity when of the wheel at 2 seconds, okay? So this is the starting angular velocity, but this is, you wanna know the final angular velocity. And then C, what is the angular displacement result while the angular velocity found in part B doubled? I don't think we need to do C, let's just do A and B, okay? So in A and B, we basically need to know the angles being rotated and then the final angular velocity, okay? So what we're given, again, let's start from drawing a picture. So this is example 7.2. So let's draw this view here, okay? Like this, you know. And okay, the wheel is rotating. So what we know here is, what we're given is the initial angular velocity, which is 2 meters per second, 2 radian per second. Omega I equal to 2 radian per second, okay? Because it is positive, that means the wheel is rotating along the positive direction, which is counterclockwise direction, like this. We're also given the angular acceleration, which is a constant, to be 3.5, okay, radian per second square. So we're giving this two pieces of information here, okay? And then in part A, we were looking for the angle has been rotated during this, okay, sorry, we also know the time, which is 2 seconds, okay? From 0 second to 2 seconds, okay? So we want to know delta displacement, delta theta in this 2 seconds, and then we also want to calculate the final angular velocity, omega f, okay? Okay, we're giving these three pieces of information. Again, solving this kind of problem is kind of similar to what we did in chapter 2. You draw a nice picture, you make sure you know what's going on. Because there's angular acceleration, and the angular velocity initially is positive, so this is gonna go counterclockwise, but it's gonna speed up, okay? Rotating faster and faster and faster, okay? Now we're given these three pieces of information, so you need to write them down clearly or near the figure so you know what you know. And then you write what you want to find out as well. And then the next step is to basically find a formula that connecting those three pieces to the one that you want to find out, okay? Well, because we want to get delta theta, right? Certainly we want to get one of these three, right? Now, what do we know here? We know omega I, we know alpha, and we know delta t. So which formula do you think is the best to solve this problem? I mean, just tell me number. If this is 1, 2, 3, 4, which formula do you think is best to get delta theta? Okay, got one answer here.
3.
Okay, somebody says 3. 3. Okay, got two answers. 3. Okay, both. I guess everybody agrees it's 3. So yeah, if you look at 3, right? We have omega I, alpha, delta t. We have everything. So 3 is the best. Okay, this one not working because we don't know omega f. Same thing for this one. So let's use 3 then. Okay, we have delta theta equals to omega I delta t plus 1/2 a alpha delta t squared. Okay, so plugging numbers, we have 2 radian per second times 2 seconds plus 1/2 alpha, which is 3.5 radian per second squared times delta t squared, which is 2 seconds squared. Okay. Now notice units second cancel out. This is radian per second squared times second squared cancel out. So it's radian as well. So in the end, you have 4. This is 4 plus. So they have 2 squared, which is 4 divided by 2, which is 2 times 3.5, which is 7. So 4 plus 7 radian. Okay, so that's basically 11 radian. Okay, so that's your answer in radians. Okay, now also ask you to give the answer in revolutions. Okay, the reason for that is revolution is a little more intuitive. So certainly 1 revolution means one circle, right? Well, that certainly means 2 pi radian, right? 2 pi radian, because 1 circle is 2 pi radian. So you have 11 radian here. You can easily convert it. So 11 radian times 1/2 pi, okay? A revolution per radian divided by radian, right? So that give you, so 11 divided by 2 pi is your revolution, okay? Well, you can do a calculation, 11 divided by 6.28. So it's like 1.75, okay, 1.75 revolution. So that certainly is more intuitive. So you see that during this 2 seconds, the wheel finished the full turn and then it finished another 3/4. Okay, so that's this. Okay. Now let's do the second part. The second part, we need to find out the final angular velocity. So which formula do you think is the best to do that?
The first one.
Yes, you can definitely use the first one. And actually, since we know delta theta now, all of these actually works because we see there's only one unknown in this one. I mean, this one is not working, sorry, because there's no omega f, but this one's working as well. But this one is simplest to use. So let's use the first one, okay? So omega f equals to omega I plus alpha delta t. Just plug in numbers. This is 2 radian per second. The alpha here is 3.5 radian per second square. And delta t is 2 seconds, okay? So, well, this 1 second cancels out one of these. So you have radian per second as your unit. And then the number here, you have 2 plus 3.5 times 2, which is 7, so it's 9. So 9 radian per second. So that's your final angular velocity. Any questions about this problem? It is pretty simple, right? Yeah, I think it's pretty simple. And I mean, you can tell after you went through the first round, you know, chapter 2, chapter 3 stuff, when you do the second round about the same kind of stuff, everything becomes easier, you know. And as you can tell now, why I'm so smart in this class, simply because I went through everything for like 100 times. Maybe not 100, but very close to be 100 times. So this stuff here for me is really like no brainer. I can just, because I've been through it so many times. So anyway, so same thing for you. The more you practice, the more you do stuff, the more familiar it is gonna be for you as well. So we're done with this, the second part, the specific rotation part, okay? So today, let's do another part, and then we'll see whether we can do an exercise on this. So the third part is called a relation between linear and angular quantities. So our so this is the last part before we go to dynamics, okay, of a little bit dynamics of this chapter. And okay, so what are we talking about here? So the question is this, okay? As we said in chapter 2, we could use quantities like displacement, velocity, and acceleration to describe motions in general, which means for any motions. Well, in this chapter, we learned about angular quantities like delta, theta, omega, and alpha, right? Then the question is, what are the relations between them? And why do we prefer to use this set of quantities instead of the previous set, okay? So that's something we want to address, which is actually also very interesting by itself. So let's again look at a very simple rotation, which our friend of like a 2D rotation on the circle. Say you have a particle here, okay? Let's focus on one specific part of the motion. Let's say the particle goes from here to here, like this. And so we use, let's try to use, okay, the angular displacement here would be like delta theta, right? And then let's say the radius is r, okay? So let's start connecting them now, okay? According to the definition of radian, right? Delta theta would be equals to the arc length here, s, divided by the radius r, right? This is simply the definition of radian, right? As we just discussed. So given that, we can then go ahead and find out all the relations. So take this equation here, divided by delta t on both sides. So what do we got? Okay, on the left-hand side, we got delta theta over delta t. On the right-hand side, we got s over r delta t, okay? Okay, what is on the left? Okay, what is on the left simply is the definition of angular velocity, so omega here, okay? What is on the right? Okay, what is s divided by delta t? So s here is the arc length that's traveled by the object. Well, delta t is the time it takes to travel that distance. So distance divided by time, it simply give us the speed of the linear speed of this motion. So it's be v here, okay? Now, strictly speaking, I need to put an absolute value here for both of these two, okay? Because we really talk about the speed, not the velocity here. We better call this angular speed. And this part here is our linear speed, okay? Because the direction of them are very different, okay? The angular speed, okay, this is going along this like this. Well, the linear, linear velocity here is actually changing direction all the time. It's going like this, okay? So, we didn't even talk about, yeah, let's forget about that part. But basically, this formula here tells us the relation between these two speeds, okay? Now, for simplicity, we will just write them like this, but you need to keep in mind, this is good for this, the magnitude of these two quantities, okay? Without errors on top of them, okay? So these are magnitudes. So we got our first relation between these two. Actually, this is a relation as well, right? There's a relation between the angular displacement and the distance, okay? Okay, so you can go further. If you take delta, because these are related like this, so the change of angular velocities are going to be related to the change of velocity divided by r, okay? And if you take another division to delta t on both sides, you got delta omega over delta t equals to delta v over delta t times r. Well, okay, this is nothing but our angular acceleration. What about this, delta v over delta t? It's going to be our acceleration. So it's going to be a over r. Okay, now specifically, this is going to be called tangential acceleration. It's the acceleration along the tangential direction, because that's the how much the speed changed here, okay? So that's give us the third relation, okay? Out of these three, I would say this one is probably the most important one. And this one exists, but we don't use it that much. Well, this one is commonly very useful to know, omega equals v over r. Sometimes people write this like v equals to omega r as well, but it's certainly the same thing, you know. Omega to v over r or v equals to omega r, the same thing, okay? So, so what does that tell us, okay? It tells us something really interesting, okay? For example, let's consider a merry-go-round, okay? Let's say the merry-go-round rotating like this with constant omega. Based on this relation, what can you say about its linear speed? Because linear speed equals to omega times r, that means at different position, the linear speeds are all different, okay? Basically, the further away it is from the rotational center O, the bigger the linear speed will be, okay? And it's proportional to the radius, okay, because of this relation here, okay? So this explains why when you're on the merry-go-round, if you're around the center, you don't feel much dizzy, you know, you don't feel moving that much, but when you're at the edge, you feel it really goes really fast, okay? So that's simply because even for the simple case of a constant omega here, we have a bunch of different linear speed, okay? And they are related, they're proportional to the radius. And this actually also explains why we want to use omega instead of v to describe the motion, okay? For a continuous mass distribution like a merry-go-round, to use v would be too much because it requires you to describe every single point with different velocities, you're staying away from the center. But if we use omega, a single value is enough, is sufficient for constant omega here, okay? Does that make sense to you guys? Well, if you consider the previous case, like a single particle rotating on a circle, there's not much difference because for a single particle, it has a fixed length, fixed radius to the center, and then the velocity is just a one number. I mean, and the angular velocity is also one number. So in this case, it's equivalent. But for a continuous mass distribution, like a merry-go-round, or wait, this will be here, okay, or like a wheel, you know, or a cylinder or a ball, it's all like easier to describe these motions by using omega instead of v, okay? Does that make sense to you guys? Give me some up, please. I mean,
Yeah.
right now I cannot see any of you, so it's kind of hard for me to know whether, okay. Okay, we got one person, good. Okay, some up, okay, good. Okay, I guess we have time for one quick exercise. Let's do one exercise. Again, you guys are gonna get some bonus point, right? So that's good. So we're gonna have, let's consider this. We know the Earth's rotating, right? Let's consider somebody living on the equator here, okay? Equator of the Earth, okay? I guess for that purpose, it doesn't matter. Okay, yeah. So the question here is, what is the angular speed of the rotation? Of Earth's rotation. And then the second question is, what is the linear speed for a person at the equator? Now, how do we do this? Okay, again, we can only do the, let me give you some hints. So for the angular speed or angular velocity, we go back to the definition here. Okay, we got delta theta over delta t, right? So we can take a certain amount of displacement by Earth, angular displacement divided by the time, we can get it. Okay, so how do we, what do we do here? What is the period of the rotation? How long does it take for Earth to rotate one circle?
1 day.
1 day, right? So you can convert that to a second. That'd be your time. So how much angle is rotated during that 1 day?
360.
Right. So which is 2 pi in radians. So we from there we can get 2 pi. That's our angular displacement, and then that's our whatever time it is. 1 day you convert it to a second, and then you can calculate your angular speed here. Okay. Now for the linear speed, we need to use this formula here. So I need to give you the radius of the Earth. Okay. So let me look it up. Okay. So go ahead and calculate the angular speed for now. Okay. And send me your answer. Okay. Okay, I'll put like again, you can convert it to a meter per second. Okay, so anyway, the radius, so send me the answer for the angular speed first, and then I give you the radius of the Earth at the equator. This is 6,378 kilogram, and then from there you can calculate the linear speed. Well, certainly if you don't get the angular speed right, there's no point to get the linear speed. So try to do this one first, okay? It shouldn't be that bad, right? What? Yeah, just send me your answer here, okay? If you got it right, first part, go to the second part. Yeah, remember we're doing radian per second, so you need to go do everything about radian, you know, like because the unit for angular velocity is radians. Okay. Okay, I guess let's just talk about a little bit. Okay. Because this is a simple thing, and you guys already tried. So the first part is just like very simple, right? So to take a angular, so omega, take omega with delta theta or delta t. So which is gonna be like 2 pi in radian divided by 1 day. Well, 1 day is 24 hours, and each hour is 3,600 seconds. So this will be the ratio. Okay. So if you take this, you get 7.27 times 10 to the negative fifths, okay, radian per second, okay. So this is really a tiny angular speed. Compare with the example we did here. See, this view start from like 2 radian per second and go all the way to like 9 radian per second. This angular speed is really nothing, you know. But let's calculate the angular, I mean the linear speed v here, okay, for the person on the equator, okay. So v equals to omega r. Well, just take 7.27 times 10 to the negative fifths radian per second multiplied by the radius of the Earth, which is on the equator 6378 times 10 to the third. That's like meters, right? So this is a kilometer, this is a meter. Well, the unit you got is radian times meter per second, but radian is not really like a real unit, so you got a unit in meter per second, okay? If you multiply this together, I got like a 464 meter per second. Is that something you guys got as well? Roughly 464.
That's what I would have gotten. I just didn't realize it was times 10 to the third.
Oh, okay. Okay. Yeah. Well, this one seems like pretty large, right? Well, we were moving like 400 meter per second or something, you know, for a person living on the equator. But we don't feel it. The reason for that is first of all, we're moving with constant speed, and secondly, everything's moving with us. The air, the atmosphere, I mean the trees, I mean the house, the tree, the air around us, everything's moving together. So we don't feel that, but it's actually pretty big linear velocity, right? Like in terms of absolute sense. So there used to be some people suggesting the easy way to travel is like if you just shoot a rocket go out of the atmosphere and then just wait there for a while, and then the Earth's gonna rotate, right? And then you come back, then you go to a different place, like really quick, you know. See, because of this really big speed here, right? And another thing you notice here is this is not true universally, because the axis here, so the equators, I mean on the equator the radius is largest. As you're going toward the North Pole or South Pole, this speed is getting smaller and smaller because the distance from that surface to the axle is getting shorter and shorter. And strictly speaking, when you're standing right on the North Pole, you don't have any linear velocity because radius r is 0 at that point. So I think we're in a altitude about like I don't know, even 30 degree maybe towards the north, or maybe different. But well, certainly we'll have a way smaller linear velocity here. But the whole Earth have a single angular speed, can all be described by this number. It's by this really small number. Okay. Okay. So I guess that's all I want to say today. Do you guys have any questions for me?